All right, so next up is four attached things. So if you think about four attached things, most of the time people are going to think square, right? Then be like, oh, okay, there we go. They're far apart as possible. This is actually incorrect. So we say no. And think about why this is incorrect. We're drawing this on a two-dimensional piece of paper, but in the real world, these molecules exist in a three-dimensional world. So there's ways to get them further apart by using that third dimension. And so, right, we have four attached things, so we're thinking about AX4. And so it's kind of like you take the square and then you take 2 points and rotate them about 90 degrees. So take a look at the top right here in this GIF. You can see what it looks like. You're going from square to tetrahedral. So Google square to tetrahedral if you want to kind of figure the shape out. Let's go back to this one, right? And now let's attach. There's 3 bonds, and then we add the 4th one, and you see we have what's known as a tetrahedral. So it looks kind of like that triangle thing, except now there's one on top, and there's stuff being pushed out. So you can see this really is a 3-dimensional thing. So let's put it like this, where this top and bottom left one are in the plane of the board, and then you see one molecule, this guy back here that I'm wiggling, is behind the board, and then this guy right here that I'm wiggling is in front of the board. So let's see how we're going to draw that. So an example of a tetrahedral molecule is CH4, right? You've got a central carbon and then 4 hydrogens attached to it. So we draw we draw 2 of them in the board, just like we see in this image. And then one's going in front, and then the other one is going in back. So the way we symbolize that is by using wedges and dashes. So when you have these dashes, that means that it's going behind the board. And then when you have this wedge, that means that it's going in front of the board, or it's coming out of the board. So going into board or plane or whatever you want to think about it, and then this one is coming out. Right, so it looks just like this. That's how we draw this 3-dimensional structure on a 2-dimensional piece of paper. And then if you take a look at the bond angles, they're all 109.5. And again, this is called tetrahedral. And since we have no lone pairs, both the molecule geometry and the electron geometry are classified as tetrahedral, right? But now what we can do is we can replace one of these atoms with a lone pair and kind of get this formula of AX3E, where we still have 4 attached things, but now 3 are atoms, 1 is a lone pair. So this is ammonia, NH3. Has this shape, and so if you draw this, you draw nitrogen, we'll put the lone pair poking out of here, 1 hydrogen in the plane of the board, 1 hydrogen coming out, and 1 hydrogen going into the board. And then remember, lone pairs repel more than bonds, and so we say this bond angle is less than 109.5 degrees. And now it's going to have 2 different geometries, an electron geometry, which considers the lone pairs as kind of being there, and a molecule geometry where we kind of pretend the lone pairs aren't part of the shape. So the electron geometry stays the same. It's still a tetrahedral because, you know, it's the same then as CH4 if you're considering your lone pair as a thing. And then the molecule geometry is what's known as a trigonal, because the bottom part's like a triangle, and then pyramidal. I don't know if I spelled that right, because it's kind of like a pyramid. So let's take a look at our model. So we'll take out one of these lone pairs, or one of these bonds, and put in a lone pair. And so you can see you've got a triangle down on the bottom, and it looks like a pyramid. So trigonal pyramidal. Again, you see this model points at 109.5 degrees, but if we take a look at the real molecule, should have NH3. Yep, there's NH3. You can see all of the bond angles are less than 109.5, right? And so molecule geometry, trigonal pyramidal, electron geometry, tetrahedral. And so we can go even to more shapes, right? What if we replaced yet another atom with a lone pair? So now we're in this form of AX2E2, right? 2 atoms, two lone pairs. Water is going to be an example of this. And so it's still kind of overall this tetrahedral shape, but this is the way water is generally drawn. It's generally drawn with the electrons kind of looking as though they're both in the plane. But in reality, one of them is kind of coming out of the plane, and then one of them is going into the plane. But this is generally the way it's drawn. And remember, lone pairs repel more than single bonds, so we say this bond is less than 109.5 degrees. The electron geometry, still tetrahedral. Now we call the molecule geometry as bent. So same name as the previous bent, but a different bond angle, right? Before the bond angle there was less than 120, now it's less than 109.5. So let's take a look at that. Take a look at our model, get rid of one of these bonds, and then add a lone pair. So you see it still has that tetrahedral shape. And you can see our kind of two-dimensional drawing of water isn't quite as accurate as what it really is, because one of these lone pairs is going in and out of the bond, but that's generally the way water is drawn. And then if you take a look at real water, you can see the bond angle is less than 109.5. And again, molecule geometry bent, electron geometry tetrahedral.